All right, so I am back again after seeing the first segment of the video that I recorded previously. Everything looks to be okay, so I'm gonna carry right on. Got my tea mug to help me now as well, and let's jump back in. All right, so what we did up until now was basically spend 15 minutes talking about this slide and creating a basic statistical model for how to generate a sequence of count data where we're using the running example of text as our source of count data, where the individual elements that we're counting are individual terms in documents. So what we want to do now is talk about ways of estimating the model parameters, which are these multinomial probabilities, which represent the probability of seeing terms in text. Now, on this slide, we are setting up a maximum likelihood problem. So we're going to begin with the likelihood function. All right, so given some data that's available to me, these collection of term counts in a document, I can write down the probability of having observed those term counts given the underlying multinomial probability vector, and that is exactly this expression. So to give, I guess, a little bit of motivation for where this expression came from, because the probabilities of the individual elements in a list are independent, I can basically just multiply all the individual probabilities together. So if I have a list which is 2, 1, 2, 3, 3, and that's the document that I have available. What's the probability of observing a 2 in the first slot? Well, that's a beta 2. What's the probability of observing a 1 in the second slot? That's a beta 1. All right, and so on and so on and so on. So I multiply together beta 2, beta 1, beta 2, beta 3, beta 3. And so the likelihood function to the left of this little example simply is the generalization of this idea of multiplying together a bunch of individual probabilities. All right, so I would take the 2 beta 3s and multiply them together. That would give me beta 3 squared. I would take the 2 beta 2s together, and that would give me beta 2 squared, and then I have beta 1 by itself. All right, so this likelihood just takes the product over all individual terms. I look at the number of times that those terms appeared in my list, and then I exponentiate the probability of observing that term by the number of times that it is actually in my data set. Okay. All right, so I'm not here to give a full course on statistics, but maximum likelihood is a very classical approach to inference in which I take this likelihood function and I maximize it, all right, with respect to the parameters beta. The resulting estimates have nice properties, which I'll let you go read about in a textbook. But if you've taken any sort of graduate level econometrics, I assume that you are familiar with this. The only, maybe I don't know whether non-standard is even the right term, but the only thing to bear in mind is that there's a constraint on these parameters. All right, so if I form this log likelihood function from the above likelihood function, I don't directly maximize the log likelihood. I also take into account that there is a constraint on the parameters that I am maximizing with respect to. And that constraint is that these betas have to form a probability vector. All right, so I am including a sum to 1 constraint in the maximum likelihood problem, and there's a Lagrange multiplier associated with that constraint. Now, if you wanted to be, fully transparent, there should also be a whole set of constraints that constrain the individual betas to be between 0 and 1. But we're going to ignore those constraints and show that the solution to this problem with just the probability vector constraint will also satisfy those other constraints. Okay. So beginning with this Lagrangian, which represents the constrained maximum likelihood problem, I can take first order conditions. All right. So there's a first order condition for each of the capital V parameters. So this here is really a set of capital V equations. So each individual probability is equal to the number of times that term V shows up in the list divided by the Lagrange multiplier. Okay. So how am I going to get out the value of the Lagrange multiplier? Well, I can take, I can take these capital V equations and sum them together, right? So if I sum together all of these V equations, the left-hand sides are going to sum to 1 because we know that these are probability vectors. So in this expression, I've sort of flipped around the left and the right-hand sides. So that 1 right there is coming from summing these betas up across the capital V equations. And then when I sum these up, these xv divided by lambda, I'm going to generate this sum, all right? And what is the sum over all of the terms in my document? Well, that's just the number of slots in my list, all right? And I call the number of slots in my list capital N. All right, so that's just how much how much data I have, how long this list is. So I'm going to go plug in the value capital N for the Lagrange multiplier, and that's going to give me my point estimates for the individual betas. Okay, so pretty straightforward maximization problem. Let's not get lost in these details. Let's just focus, I think, most importantly, on this last bullet point, which is these MLE estimates have a very natural interpretation. All right, so they are simply the empirical frequency of terms in my data. Okay, so XV divided by N is the fraction of slots in my list that are occupied by term V. All right, so I'm going to take the empirical frequency of my terms in my data and use the betas are simply matching those empirical frequencies. So you can kind of think of this as a moment matching condition as well if you want. Okay. So that's I guess a very natural starting point. If you want to generate a statistical model for text, I look at the empirical frequencies of terms and then basically predict new terms if I wanted to do so using that empirical frequency. Okay, now let's think about that approach to inference in a high-dimensional setting. Okay, so this is an example I like to use. So let's say that you go into the inference problem, and now I'm using a specific setting that's laid out in this slide. So let's say that we know that capital V is 10,000. Okay, so this is now a high-dimensional problem in the sense that we have many possible features that might appear in our textual data in our document, in our list of terms. And the specific example that I'm using here is of the Portuguese language. All right, so let's assume that you don't speak Portuguese. You know that there are 10,000 terms in Portuguese, and you're trying to do inference on the probability distribution of those terms in a Portuguese document. Okay. Now, the data that you have available to you is a single snippet of text, and I'm not going to try to pronounce this, but I think I found this on Google Translate, all right, which is they drink. All right, so that's the Portuguese for they drink. And we can think about this again as a list. All right, so we have how do we say this? LLS Bebum. And I want to estimate beta 1, beta 2, beta 3, beta 4, beta 5, all the way up to beta 10,000 using this data and the maximum likelihood formula from the previous slides. Well, what am I going to do? N equals 2, because that's the number of words that I have available to me. And each one shows up once. So the beta for LS is going to be 1/2. The beta for Bebum is also going to be 1/2. And the beta V is going to be 0 for all other V. All right, so we have matched the multinomial probability vector to the empirical frequency of words that we had available to us when we were conducting inference. Now, at this point, it's usually useful to stop and get people's reactions to this model. I think intuitively, most of us understand that this is not a reasonable approach to inference in this setting. I mean, it might have statistical guarantees in some theoretical sense, but intuitively, there are some problems here, right? So first of all, we know, and here I'm putting "know" in quotations because I'm speaking loosely, we know that working languages contain a variety of words, right? So presumably there are hundreds of words that are used in the Portuguese language on an everyday basis as people communicate with each other, okay? So that's one sense in which this is a strange set of point estimates for this language model, okay? So we can go a little further. We also, quote unquote, know that word frequencies in language tend to be highly skewed. All right, so we don't usually have uniform distributions over the set of words that do appear, right? Typically, some words are used much more than others, whereas this is a uniform distribution, 50-50, over the words that they get positive probability, okay? We know that Portuguese is similar to Spanish, and so this is not really how Spanish would look, and so on and so on. So what's the problem here? Well, this happens all the time in machine learning. So if you've had any background in machine learning, you know that when we try to do inference on many parameters, so I had a little interruption here, but I will carry right on. So the issue here is overfitting. Okay, we have 10,000 parameters that we're trying to learn, and we essentially have 2 data points that we are using to learn or estimate those parameters. And so I use learn and estimate kind of interchangeably because I both read the computer science literature and the econometrics literature, and they basically mean something very similar. So that's why I use them more or less interchangeably. All right, so the challenge is, how do I avoid overfitting? So the standard answer in machine learning is that I use regularization, right? I somehow want to not have so much weight put on the limited data available to me when I form my estimates. And there are many ways of doing regularization, and you may have learned about some of them yourself when you've taken machine learning courses. Here, I want to focus on a particular kind of regularization, and that is regularization based on this paragraph right here. All right, the idea that you come into a problem understanding something about its structure, and you want to use your understanding of your beliefs about its structure to limit the influence of the limited data available on the parameter estimates. And the way of formalizing the idea that you can use these initial beliefs to regularize the problem is formalized with Bayesian inference. Okay, so I sort of think about Bayesian inference in the context of machine learning as a statistical regularization technique that's informed by your beliefs on the structure of the problem that you are trying to study. Now, I know from various conversations with colleagues at UCL and other places, and also from reading different textbooks, going to different seminars, that there are varying beliefs on the utility of Bayesian techniques, right? So some of these conversations get a little bit philosophical, and there are ongoing disagreements about the role of Bayesian statistics and econometrics and in other fields. I'm not here to open this big debate and this big discussion about whether we should be using Bayesian methods in general, or what the strengths and weaknesses are of Bayesian versus frequentist approaches. I'm here to make a narrower point. I guess the first thing I'm trying to do is to introduce to you the idea of Bayesian inference, because it is quite common in statistical machine learning. The second thing I'm trying to do is, I guess, convince you that it is an approach to regularization. It might not be the best approach to regularization, but it has the effect of limiting the influence of the data on the outputs, on the estimation outputs. Okay, so Bayesian inference begins with Bayes' rule, and if you ever forget Bayes' rule, it's fairly easy to derive. So let's say that I begin with a joint distribution over random variables A and B, or sets of random variables A and B. I know that I can factor a joint distribution as follows, right? So I could factor the joint over A and B as the conditional distribution of A given B times the marginal distribution of B. But I could also factor it another way. So I could factor it as the conditional distribution of B given A times the distribution over A. Bayes' rule is just equating both factorizations together and dividing one side by the marginal distribution. Okay. So from this, I immediately obtain that, where this particular one would be the joint distribution over my count data X and my parameter vector beta. Okay, so I'm just, you can apply this formula to the joint distribution over the data and the parameters. Now this thing has a name, all right? So the distribution of the multinomial probability vector given the observed count data is called the posterior distribution over beta. Okay, so after I observe this data X, I have a distribution over the betas. Okay, now where does that distribution come from? It comes from two different sources of information. So the first source of information is the conditional distribution of X given beta. All right, well, this thing, the conditional distribution of X given beta, is exactly what we were working with here in slide 3. So my notation is a little bit off. Okay, so probably in this slide I should have called this P of X given beta. But that is exactly the likelihood function. All right, so one source of information about this posterior belief I have about the multinomial probability vector is the likelihood function. So you can think of that as the contribution of the data to this posterior belief. Well, the other source of information I have is this P of beta. Now that does not depend on data. All right, so this is called the prior distribution. So this is whatever initial belief I have about how beta should be structured in this problem. So this is where I would pack in all of these ideas that, for example, I think beta should be non-negative for most, if not all terms. Right? That's where you would encode that belief. Could also encode the belief, I think the beta should be skewed so that relatively few terms get most of the probability, and then there's a long tail of low probability terms. You could encode that belief in here too, all right? And then your final posterior is going to combine this initial belief over beta with whatever information the likelihood provides about the betas given the data. And those two things combine to generate this posterior distribution, okay? The denominator is the marginal distribution over the data itself. I don't have a deep interpretation of that, except it's a normalizing constant, okay? So in fact, you sometimes see Bayes' rule written down as the posterior belief of the parameters given the data being proportional to the likelihood times the prior, all right? And then it's understood that the posterior needs some normalizing constant, and that turns out to be this evidence, which is the marginal distribution over the data, okay? And that's it. Okay, we can, we could sit and philosophize about this for a while, I guess, if we wanted. So for example, one of the conceptual differences in Bayesian inference compared to frequentist inference is that these betas are considered to be random variables, not unknown fixed parameters, right? So you begin with some belief over the betas, treating them as random variables with this distribution given by your prior. You then see data and you have a new distribution over the betas. But in both cases, beta remains a random variable. It's just that your beliefs about that random variable are shifting around. Okay, so we don't consider the betas to be some fixed unknown constant, right? All right, so that is, I guess, a probability statement, right? That I can decompose a joint distribution over data and model parameters in this way using Bayes' rule. So you can think of it as an accounting rule about where probabilities have to go in this joint distribution. The more interesting part of the exercise is that you can actually use this to do statistical inference. And so the question is, how would I use this probability decomposition to do inference? So there's a few ways of doing that. Let me flip back to my whiteboard. All right, so let's say that I start with a prior distribution over beta, beta 1, the first term in my language model. So we're going to talk about where the prior distribution comes from in a minute, but for now, just allow me to write down some distribution over 0 and 1. All right, so it might look like that. Okay, so that's my prior. Then I'm going to get new data. I'm going to see new data, and that distribution is going to shift. All right, so let's say that I get some data that suggests to me that 1 is less likely than I originally thought. All right, so this would be my posterior. Now I can take this posterior distribution and start doing inference on beta 1, right? And there's a few ways that I can report a Bayesian estimate of beta 1 under the posterior. So one thing I could do is report the point at which the posterior distribution is maximal. All right, so that's sometimes called the map estimate. Hold on, I guess. Not sure what the notation in the slides say, but for this whiteboard, I'll write that. Okay, so it's basically the, I think MAP stands for maximum a posteriori, which is a fancy way of saying it's the modal value of the posterior distribution. The second thing you could do is you can compute the expected value of beta 1 under the posterior. Okay, so you would integrate over, you would integrate over 0 to 1, beta 1 times the posterior distribution of beta 1 given the data. And that would give you the expected value of beta 1 under this posterior distribution. Fine. You can also report what are called credible intervals, which is the probability that beta 1 falls in an interval. All right, so you could, for example, define an interval around the map estimate. So here I'm just making up numbers, but say that's 0.1 and that's 0.3. You could say, what's the probability that beta 1 falls between 0.1 and 0.3? And you would basically take the integral and you could integrate from 0.1 to 0.3. Okay, so that would define this area. And then you can make belief statements of the sort. What probability do you attach to the probability that term 1 is between 0.1 and 0.3, and this is a number? Okay? That is not the same thing as a confidence interval. All right, a confidence interval has a different interpretation. Sometimes there is some sloppiness, so people take a frequentist confidence interval and describe it as a belief statement over the interval that a unknown parameter has to fall in, but in fact, it is something somewhat different. Okay. All right, so let me jump back into the slides. So basically, the bottom line is, if I can compute the posterior distribution, I can start to do Bayesian inference. Okay. Why you would want to do Bayesian inference instead of frequentist inference is still, is still an open question. But hopefully, I can convince you in the next, 5 or 10 slides that it might be a good idea in this particular environment. All right, so a lot of Bayesian statistics turns out to be computational because obtaining the posterior distribution, especially in high dimensional settings, turns out to be a complex problem. So there are not very many interesting models in which the posterior distribution can be tractably computed. I mean, there are special cases, and I'm about to tell you about a special case now. But in most real models, you have to rely on approximation algorithms for obtaining the posterior. But one way of simplifying your life, computationally anyway, is to strategically choose your prior distribution so that computation is easy. Let's put easy in quotations. So a popular choice for a prior distribution is that it be so-called conjugate. All right, so conjugate means that the prior and posterior distributions lie in the same family given the likelihood function. All right, so the most, I guess, well-known example of a conjugate prior is if you're trying to do inference on the mean of a normal distribution, then you can give it a normally distributed prior, and your belief about the mean in the posterior is going to remain a normal distribution. Okay. So there's in fact, a result in statistics that all distributions in the exponential family have a conjugate prior. All right. So in principle, for most models that one would use in an applied statistics context, you would, in principle, be able to obtain a conjugate prior. Another question is that prior distribution, at all reasonable or interpretable for the problem that you have in mind? Okay. So we don't always use a prior distribution that's conjugate, even though in principle we could if we're working within the exponential family. So within the framework of the simple text model that we have been developing, there is a conjugate prior distribution for the multinomial model, and that's called the Dirichlet distribution, which I will talk about in a minute. So just to be kind of clear about this, when we're talking about conjugate priors, I'm talking about choosing a family in which the prior has to live. All right. So when we say that the Dirichlet is conjugate to the categorical multinomial distribution, so we might want to use the Dirichlet prior, I still have not specified the particular Dirichlet, right? That's an important distinction. So conjugate prior is about specifying a family, not about specifying the member of the family, right? So let me, so hyperparameters are going to determine the particular instance of the prior distribution that I'm going to use in a particular problem. So to be clear, hyperparameters are parameterizations of the prior. Okay. All right, so let's talk about this Dirichlet distribution. It is, for those of you who maybe have studied a little bit of Bayesian statistics, you maybe have done this, inference on a mean of a normal distribution, which is endowed with a normally distributed prior. If you've worked with discrete data, it's often common to use the beta binomial model. All right, so the beta distribution turns out to be conjugate to the binomial probability in the beta binomial model. So this is sort of a multivariate generalization of the beta binomial. It is instead the Dirichlet multinomial. Right? So just like the multinomial is the multivariate generalization of a binomial distribution, the Dirichlet is the multivariate generalization of a beta distribution. Before we get into the particular notation, let me just conceptually describe what a prior distribution in our text model does, or what structure it has. So I'm getting lost. Okay, there we go. All right, so the most high dimensional problem I can write down on a whiteboard is a three-dimensional model. Okay, now, of course, the actual model that we're considering has capital V dimensions, but let's take V equals 3 for this running example. So we have beta 1, beta 2, and beta 3. Okay. So I'm trying to search in this beta 1, beta 2, beta 3 space for my language model. All right, so I know that I have to restrict the beta 1, the beta 2, and the beta 3 to be probability vectors, which basically means it has to lie in this triangle inside the three-dimensional reals. All right, so sometimes this thing is called the simplex. It's the set of all probability vectors in R3. Right, and it's actually a two-dimensional space. It's this triangle that lies within R3. And the corners of the simplex are going to be 1, 0, 0, 0, 1, 0, and 0, 0, 1. All right, so I'm gonna take this simplex out of the three-dimensional reals and collapse it down into just a flat plane. Okay, so I don't have to keep working in the three-dimensional reals. So let's say that this is 0, 1, 0. This is 0, 0, 1, and this is 1, 0, 0. Our language model has to be an element of the simplex. All right, so for example, I could have a language model right in the center of the simplex, 1/3, 1/3, 1/3. Right? I could also have a different language model that put less probability, and so I have to make sure I align everything correctly. So if I moved vertically up this simplex, I would be putting more probability on the second term and symmetrically less probabilities on the first and the third term. So this might be, for example, 1/4, 1/2, 1/4. Okay. But basically, every point I move in this simplex is going to give me a new language model. And the maximum likelihood estimates would choose one point on this simplex as the point estimates for the probabilities of terms 1, 2, and 3. Okay? A prior distribution, so this Dirichlet prior distribution, is going to endow this simplex with a full distribution. All right, so I am going to no longer have, individual points here as sort of, my belief about where my language model is not going to be a fixed point in here. It's going to be a distribution over this space. All right, so my Dirichlet prior is a distribution over the simplex. Okay, now it might put more mass on the corners, it might put more mass in the center, it might put more mass on the edges, whatever, okay? But the key point is I have a belief over all possible language models, all right? So a particular language model would be a point in this space, and I now have a belief over all of these things, okay? And my prior distribution is going to be a distribution over this simplex. I'm then going to see data, and I'm going to have a posterior distribution that's also defined on this simplex, but it's going to be putting mass in different places according to where I saw more and less data. Okay, so that's the big picture. And here you go. So this slide gives to you the algebraic definition of the Dirichlet. All right, so it's proportional to the product of individual betas. Okay, so here I'm defining a distribution over the multinomial given these things. So these eta things are hyperparameters, and they define a particular Dirichlet distribution. All right, so and there are in total capital V of these hyperparameters. Okay. And given those hyperparameters, I'm going to have a distribution over the multinomial beta vector. And that distribution is going to be proportional to the product of the betas. There's a normalizing constant here, which makes the Dirichlet integrate to 1, but we can ignore that. Okay, I'm not gonna say anything about that. All right, so if you compute the marginal distribution out of a Dirichlet, it turns out that's a beta distribution. As I said before, if you take v equals 2, so you only have 2 dimensions, then the Dirichlet is a beta, okay? And the means and the variances of the Dirichlet are given by these formulas. Okay, so basically the mean of the v random variable is the hyperparameter assigned to that dimension divided by the sum over all the hyperparameters. Okay. Now, if you're going to do Bayesian inference, you need to specify a prior distribution. And in this parametric setup, specifying a prior distribution is equivalent to specifying the hyperparameters of the Dirichlet distribution you want to use. So once you specify these etas, you have specified a particular Dirichlet, and then you're going to see data from your text, and then you'll have some new Dirichlet afterwards. Okay. So what are we going to do about specifying this set of hyperparameters? Well, one option might be to, and you don't have to do this, but it's quite common in the machine learning literature, to specify a symmetric Dirichlet. All right, so if you have no reason to favor believing that one word is more likely than another, you can set the eta v equal for all v. So that basically takes, the capital V hyperparameters that you could in principle set and collapse it down to just one hyperparameter, which is what's going to be this symmetric Dirichlet that you're going to use. Okay. You don't have to do that. If you have some reason to believe that one term is more common than another term, you can specify an asymmetric prior, should you wish. Right? But if we go back to this simpler case where we have a fully symmetric Dirichlet with just one hyperparameter that we can call eta, we then have to choose that value of eta. So it turns out that, and I'm not gonna prove this, but eta equals 1 defines a uniform distribution. So you would treat all language models as equally likely. Eta greater than 1 is going to put relatively more weight in the center of the simplex. So you're going to consider the 1/3, 1/3, 1/3 model in the previous example on the whiteboard as more likely. Eta less than 1 is going to put more and more weight on the corners of the simplex, right? So if you wanted to, for example, encode the belief that your language model is skewed towards relatively few words, you would want to use a prior distribution with eta less than 1, right? So this would promote a sparse language model in the following sense. So if that's not totally clear, let me go back here. So the eta small is going to push more prior mass away from the center and towards the edges. Sorry, towards the corners. And at these corners, you have skewed outcomes, right? So each corner represents a particular direction of the skew. So this corner has skew towards the second term. This corner has skew towards the first term, and this corner has skew towards the third term. So you're not taking a stance on, which particular dimension the skew is pushed towards. You're just specifying a prior that is going to generate skewness on one of the corners, okay, while staying agnostic on which particular corner. All right, so if you want to get a little bit more kind of visual intuition on how the Dirichlet looks, we can start with the beta. Okay, so the beta is a distribution on the basically one-dimensional simplex, right? So once we, you can think about this here as the 1D simplex, which represents probabilities in a two-dimensional space. So for example, this would be, 0.4, 0.6, right? A 40% probability on zeros and a 60% probability on ones. So eta equals 1 is a uniform distribution. So you're going to consider all probabilities equally likely. Eta equals 5 is going to push you towards the center of the simplex. So you're going to tend to have more mass on 1/2, 1/2. And eta equals 0.5 pushes you towards the edges of the simplex, where you're gonna, either be in the region of most probability on dimension 0 or most probability on dimension 1. All right, so I can't draw a 10-dimensional Dirichlet, but I can sample from it. So this slide is 4 different random draws from a 10-dimensional Dirichlet. So in this case, V would equal 10. And this gives you a sense of, where I lie on the 10-dimensional simplex in, in these 4 random draws. Okay. Now, if I start drawing from a 10-dimensional Dirichlet with eta equals 0.1, I'm not going to be drawing towards the corners of the 10-dimensional simplex, which are, going to put a lot of mass on relatively few dimensions. And you can see that that's happening in, in these draws. These are much sparser, much more skewed distributions than I had with the eta equals 1. By contrast, here's draws with eta equals 10. So now we're much closer to the uniform distribution. So a fully uniform distribution would be a straight line at 0.1, right? Because then each of the 10 dimensions would be equally likely. And you can see that we're closer to that uniform distribution here than we were with eta equals 1. If you want to go do this example yourself to convince yourself of that, if you went to like eta equals 100, then you should essentially just be drawing, flat bars whose heights are varying in a pretty tight window around 0.1. All right, but you have to make this choice, right? Like if you want to do Bayesian inference in our simple language model, you're the one who has to choose the eta. All right, so which eta are you going to choose? Is there are different approaches to this, but one I guess simple answer is that you should use an eta that you find to be reasonable or in accord with your beliefs about the world. So in a language context, I would argue that that would be a prior distribution that promotes sparsity. So this is a more reasonable language model than this. And, the particular value of eta, whether you want it to be 0.1 or 0.15 or 0.2 is in a sense less important, okay? You can do sensitivity analysis to see to what extent those choices induce in your posterior distribution. But it's typically not going to be as large as the basic choice to just make it small in some sense. All right, so let's finally do posterior inference in our language model given a Dirichlet prior distribution. All right, so I am going to apply the formula that we saw 6 slides ago. So I want to do, and I apologize, I should really clean up the notation in these slides. So where it says PR here is a little bit informal. So what I really mean is P's, okay? This PR, I guess, is more appropriate for discrete events, but the betas are not discrete, obviously. So think about these as P's. All right, so I want to derive the posterior distribution of beta given X. And I'm going to do that by combining the likelihood function with my prior distribution. Now, I've already given you the form for the likelihood function. That was in slide 2. That's what we maximized to get our MLE estimates. Right? So it's the product over all the possible terms, taking the probability of each term and exponentiating by its frequency in my documents. And then I'm going to multiply that by the prior distribution. And the prior Dirichlet is going to have this functional form. All right. So note that I have chosen to not include the normalizing constant for the Dirichlet, which could have been part of the prior distribution. And I have not included the evidence either. Okay. So the P of X. But notice that I'm not putting equals here. I'm putting proportionality signs. All right, so it's okay that I've dropped anything that does not depend on the variables that I'm doing inference with respect to. Okay, I understand that there's going to have to be some normalizing constant to make the posterior integrate to 1, but it's not going to depend on the betas themselves. All right, so when I take the product of these two things, I'm going to end up getting this, and lo and behold, what is this? Well, that's just another Dirichlet, right? Because this has the functional form of a Dirichlet distribution. I've written down a distribution for the betas given X that's proportional to the product of each individual beta exponentiated with respect to these constants. So each element of the posterior distribution is going to have the original hyperparameter, the eta V, plus the actual number of counts of term V that I saw in that dimension. So it's a posterior Dirichlet that shifted to put more mass on the dimensions where I observe more data. And where I observe less data, I take mass away, right? Which is kind of intuitive, all right? That depending on where I've seen words happen, I place more weight on those dimensions and less on unseen dimensions. But crucially, I'm never eliminating the probability of seeing any individual dimension. All right, all I'm doing is shifting my beliefs around the simplex, not creating zeros anywhere as I was doing with the maximum likelihood procedure. Okay. So I guess the punchline is, if I want to, form a Bayesian estimate of the probability of seeing the Vth term, I could use the map estimate or whatever. Here I'm taking the expected value of the beta V given the data using the Dirichlet posterior distribution and the formula for the mean of the Vth dimension of the Dirichlet, recall, is just the Vth parameter divided by the sum of all the parameters. And I'm simply applying that formula here. Okay, so this N, recall, is the sum over all the XVs. So that's where that comes from. Now this is nice, I would argue, this expression for the Bayesian estimate of beta V. So recall, what was the MLE estimate? The MLE estimate was the empirical frequency, which was XV over N. So here I have something that sort of looks like the empirical frequency, but it's been smoothed out. It's been smoothed out by these hyperparameters. So the fact that I have posterior beliefs sort of makes my posterior beliefs move towards the empirical frequency, but they don't degenerate on the empirical frequency. Okay, and that's an important distinction. So I'm moving towards the MLE estimate, but I'm not moving towards the MLE estimate immediately after I see two words. And so I always, there's some influence of whatever I thought the world should look like on how I continue to think the world looks like, although those have been modified in a way that's sort of consistent with what I would be doing in maximum likelihood inference. So this is nice because it's a statistically founded way of doing regularization. I find some of the regularization techniques in the machine learning literature a little bit ad hoc. And you might, by the way, argue that priors are ad hoc, and some people do. But at least we have a well-defined sort of statistical idea of what we're doing here, I would argue. Okay, and that can be appealing. Whether you believe that motivation or not, I hope that you understand that this setup has provided some regularization, and that regularization has come about because of this prior distribution I'm putting on what beta should look like. All right, so if you want to, formalize a little bit the idea that the more and more data I see, the more and more I should be pushed towards the maximum likelihood estimates. There's a simple little calculation you can do, which I show on this slide, which is, all right, let's take the formula for the expectation of beta and the variance of beta, which I also showed when we introduced the Dirichlet, and you can plug in the count of term V equals the sample size times the MLE estimates. All right, so I'm just plugging in everywhere I saw an XV, I'm just plugging in N times beta hat V. You take the limit as N goes to infinity, what do you find? Well, the Bayesian estimate of beta V degenerates to the MLE, and the variance degenerates to 0, okay, because you're going to end up having N cubed terms in the denominator and N squared terms in the numerator. So all that's going to go to 0. All of that is going to go to the MLE estimate. And what are we trying to say? If I see a super long document, my posterior distribution is going to get tighter and tighter and tighter around the, around the maximum likelihood estimate. All right, the more general statement is something called the Bernstein-von Mies theorem. But I think this is important because a lot of the good statistical properties of MLE estimates come about asymptotically as we see a lot of data. And in worlds where I have a lot of data, my Bayesian estimates are not going to look that different than my MLE estimates. Asymptotically, they're gonna in a sense be equivalent. Okay, and Bayesian credible intervals are going to look very much like frequentist confidence intervals, and you know, these methods aren't going to be that different. But in small samples, when I have, you know, 10 data points and 10,000 parameters to estimate, these things can diverge. And you might argue that they should diverge, okay? Because of this overfitting / regularization problem. All right, so I'm sort of done with this first pre-sectional lecture. And I think there's only one additional point to make, and that is that Bayesian regularization ideas are often implicitly used in regression models. So let's take the OLS model. Okay, so I have a set of covariates X. All right, so I'm linearly combining them with the set of regression coefficients. And I'm trying to do inference on those regression coefficients. So hopefully we all know that the OLS model has this solution X prime X inverse X prime Y. And I hope we all know that when I have many covariates, OLS is at risk of overfitting the data, right? And when I have more covariates than I do observations, the OLS solution is not well defined. Okay? So one thing I could start doing to solve these problems is endow my parameters with prior distributions. That would be the Bayesian approach to this. So let's say that I start with a regression model. And to be simple, let's say that I have a fully parametric regression model where an outcome variable is drawn from a normal distribution with the mean given by the linear combination of the covariates with the regression coefficients, and the variance is a known constant. So I could think about drawing each regression coefficient from a normal prior distribution. All right, so I have each beta I is drawn independently from a normal distribution with variance tau squared. Now, what's the posterior distribution over the regression coefficients going to look like? Well, it's going to be proportional to the likelihood times the prior. So the likelihood is going to be the probability of seeing the outcome data given the regression coefficients and the covariates. All right, so that's going to be that product of Gaussians. And then each one of the regression coefficients has its own Gaussian prior. So that right there is the prior distribution over the regression coefficients. All right, so if you want to obtain the maximum a posteriori estimate of the regression coefficients, you would basically take that and maximize it. Okay, so one initial step would be to take the logarithm of that expression and drop out any terms that don't depend on the betas. So basically the 2 sigma squared and the 2 tau squared. Actually, I should be a bit careful. So that's not exactly true. But if you take the logarithm and manipulate it, you can convince yourself that this is the resulting expression that you want to maximize. Okay. And I hope this looks familiar. So the first part of the objective function is the residual sum of squares. And the second part depends on the sum of the squared values of the regression coefficients themselves. So this thing has a name. It's called the ridge regression model. All right, where oftentimes that thing is, set at something called lambda. So here, the strength of the penalty in the ridge regression model is quote unquote microfounded as the ratio of the noise and the output over the noise that you impose on the regression coefficients. And the amount of variance in the prior distribution that you put on the regression coefficients is going to strengthen or weaken the regularization. Okay, so if tau is very small, you're basically constraining the regression coefficients to be very tight around 0, which means that you're effectively penalizing the model a lot because it's difficult in the posterior distribution to move away from 0. All right, so these ridge regression models that I think are fairly common can actually be seen as the outcome of a fully specified Bayesian model. Okay? Continuing on that same theme, you might think that the normal distribution is not as aggressive as it could be for the shape of the prior distribution on individual regression coefficients. All right, so a normal distribution is gonna look something like this. There's an alternative prior structure that you can put on regression coefficients called a Laplace distribution, or double exponential, which looks like this. So it's got this spike at 0, and so in a sense, sort of draws the regression coefficients even more tightly to 0 than a normal distribution, which is sort of constrained to have this this flat slope at 0. So if you use a Laplace distribution as your prior structure on regression coefficients, you end up getting an objective function that depends on, again, the residual sum of squares plus the sum of the absolute values of the regression coefficients. And this is called a lasso model, okay? So the only point I'm trying to make is that Bayesian ideas show up implicitly in some of the regularization schemes we already use. But one of the advantages is by making the underlying prior structure clear, you can start assessing, ways in which you might want to regularize the model in alternative ways. So I, for example, find quite attractive a prior structure. Let me, get my black color back. So both the lasso and the ridge are kind of funny models because they say, there's all regression coefficients are kind of near 0. Right? What you might actually think is, some regression coefficients are non-zero and some are 0. And then conditional on being non-zero, they may be large. Okay, who knows? So there's something called the spike and slab prior, which encodes that. All right, so again, I'm writing down a prior distribution over the jth regression coefficient. You're gonna have some probability that this thing really is 0. So that's the spike in the spike and slab prior. And then another probability that beta j is drawn from, say, a distribution that has non-negligible mass across, a big chunk of the real numbers, and that would be the slab. Okay, so that's another form of regularizing these models, which might be more attractive, right? I've also seen other variants of the slab where you get something like a distribution with 2 modes, right? So that sort of says something even stronger, which is if the beta j is non-zero, then I'm actually going to draw it from a distribution with very little mass at 0. Well, the point is, by manipulating the prior structure, you can use different assumptions about how the model looks, and that can feed down into inference, but in a way that's all been kind of made explicit by the statistical model you've written down. All right, so because I'm speaking to a blank screen, I have no idea whether anyone will or will not understand any of the last hour, but at least I hope that this was useful scene setting for some of the ideas that we will talk about in Madrid. And yes, again, let me say I look forward to seeing you soon, and I will try to make another pre-sessional video on neural networks soon. Okay, so bye-bye and see you soon.